Okay, good. Well, welcome to week 2 of general chemistry. And hopefully you got through week 1 okay. You now kind of get the sense for what this class is going to be like. And of course, I've heard from many of you and you've asked me questions. And I see that all of you are now on mastering, so that's good. I'm getting a few questions about Hayden McNeil. Remember, we're not going to start the Hayden McNeil stuff until not this week, but the following week. Okay, so you'll be hearing from your lab instructor, and any questions about labs in general should really go to your lab instructor. Okay, because they're the ones that are in charge of the labs and in charge, in particular, of your lab. So. But no, you don't have to really be on a huge hurry for that. But what you have to be doing this week is Logger Pro. Okay. And like I said, every week I'll be sending you a little checklist of things to do that week. You should be getting that on your pipeline email. So hopefully you're getting those messages from me, and you'll know pretty much exactly what to do on a week-by-week basis. Okay. Let's see. Before we get started, are there any questions? And questions during class? Use the raise hand function in Zoom, and I'll call on you. So do you have any questions before we get started? Okay, I'm not seeing any. Oh, there's no question. Nayeli.
Yeah, this is regarding the pre-lecture assignment. So there was a question having to do with like calculating like mass ratio. So I was like wondering how we do that.
Yeah, so let's see. I'm gonna talk about that a little bit today. So let me answer your question when I get to that. Is that okay?
Yeah, no worries.
Okay, yeah, I'll talk about that a little bit about today, so you can see how that works. So if I forget to do it when we talk about the law of constant composition, just raise your hand again, and I'll make sure to get to it.
Sounds good. Thank you.
Okay. Any other questions? Okay, great. So let me share my screen, and we'll get going here. All right. Can you all see my screen? Let's see. All right. So the last chapter was kind of an introduction chapter. We looked at units, and we looked at significant figures, and we talked a little bit about the scientific method, right? And now we're going to start looking at atoms and elements, right? The very building blocks of nature and the building blocks of chemistry, of course. So we'll start by just introducing a little bit about atoms and how they were discovered and sort of the history of that idea, right? Because it's a very important idea. The idea that matter is particulate, it's made of particles, is perhaps the most important scientific idea, right? Because everything ultimately is built on that, right? In 1827, this Scottish botanist named Robert Brown was looking at pollen grains in water through a microscope. And what he noticed was that the pollen grains were sort of moving around in this sort of jittery motion, right? Kind of like if they start here, they go around. And at first he thought, well, maybe those pollen grains were alive, right? But it turns out they weren't alive, because if he got other really tiny particles, that like shavings of metal and things like that, or shavings of graphite, and put them under the microscope, he noticed the same kind of jittery motion, even in things that were obviously not alive. So what was going on? Well, it took a while to understand why something would move like that wasn't alive inside of water. And it turns out the reason it was moving is because water is made of molecules, and the molecules are made of atoms, and there's thermal energy, and that's kind of jostling around. And so this little jittering particle, right, that moved around was being hit by the water molecules and the atoms within those molecules, right? Imagine sort of being, you've all been at a big graduation ceremony, right, where sometimes someone tosses out a big beach ball, And among the crowd, it just gets hit over and over, right? Have you seen that? If you've seen that, then that's kind of the same thing that was happening here, right? This is kind of like the little particle was kind of like the beach ball, and the crowd is all of the water molecules that are sort of jostling around and hitting it, right? In 1905, Einstein developed a model that explained this motion based on the particulate nature of matter, right? And in 1908, Jean Perrine did an experiment that validated and showed the model was right. In fact, he got the 1922 Nobel Prize for this. Why? It was hugely important because it established once and for all that matter was particulate, okay? That was only 100 years ago, right? Only 100 years ago did we finally establish sort of without a reasonable doubt that matter was particulate, right? That was made of atoms. It hasn't always been that way, right? We didn't always know that matter was particulate. In fact, in the early Greek times, there were a couple of philosophers that came up with the idea that matter was particulate. Leucippus and Democritus, about 5th century BC, so 2,000 years ago. Sorry, a lot more than that, right? 2,500 years ago. These two scientists said, look, if you divide matter, they weren't scientists at the time, they were philosophers, sorry. They said that if you divide matter over and over and over, you'll eventually get to these really tiny particles, which are too small to cut anymore. They can't be cut anymore. They came up with this name, atomos. Atomos. A means not to. Tomos means to cut, like tomahawk, like to cut, right? And so they thought these little particles were called atomos. And Democritus said famously, nothing exists except atoms and empty space. And so these two philosophers thought, oh yeah, matter is made of these tiny particles and there's different kinds of them, and they move through space. But this idea was rejected by sort of the big head honcho philosophers of the time. And they were Plato and Aristotle. And Plato and Aristotle said, no, that's not the way matter is. You just have to look at it and you can tell it's not particulate, it's continuous. In other words, Plato and Aristotle said, if you divide matter into smaller and smaller pieces, you can just do that forever. You'll never get to any fundamental particles, right? That matter was continuous. And what happened was that their ideas won out simply because they were so influential, okay? And those ideas lasted for 2,000 years, if you can believe it, all right? So for 2,000 years, the idea that matter was continuous was the dominating thought of how matter was, all right? That changed primarily because science emerged, modern science emerged. And how long ago did that happen? You know, it's good to have an idea for when these things happen and in your head. It's about 500 years ago or so, okay? Some historians place the beginning of modern science at the year 1543. Why that year? Because that's when Copernicus published his famous book on the revolution of heavenly orbs, right? And this book was about a sun-centered universe, right? So before Copernicus, people just looked around and they saw that the sun goes around the earth, right? Rises on one side and goes down the other. So it looks like the earth is sort of the center of the universe. And why shouldn't it be, right? Because that's where humans are, right? So we're the center of the universe and everything sort of revolved around us, right? But, excuse me, Nicholas Copernicus had one of the first telescopes, and he started looking at the sky and the stars and the planets. And he came up with a new model based on observation. And remember, the hallmark of science is this idea of observation, right? Excuse me. In Greek times, people thought that the way to knowledge was just to reason about nature, right? But at about this time, people took a different approach. They thought, in order to understand nature, it's much better to observe it, right? And begin doing observations. And then the scientific approach to knowledge, which we talked about last Monday, started to develop, okay? That's ushered in the scientific revolution, and then there was a whole bunch of progress. People you probably heard of before: Francis Bacon, Johannes Kepler, Galileo Galilei, Robert Boyle, Isaac Newton. all these people started doing work using observation. And that's how basically how science was born and developed about 500 years ago. So when did we start thinking that Plato and Aristotle were wrong? In other words, when did we start thinking about the idea that matter actually is particulate? Well, that started with Antoine, with some observations that led to laws that then led to models. So remember how the scientific method works, right? We talked about it last time. You begin with observations, right? You see something about nature, right? So Antoine Lavoisier, for example, was involved in observations on combustion, right? He burned things and he weighed the substances that were being burned before and after, right? That's an observation. And then he did that over and over, and he came up with a law. And remember what a law is. A law summarizes a bunch of observations, right? So the law that he came up with was the law of conservation of mass, right? And the law of conservation of mass says that in a chemical reaction, matter is neither created nor destroyed, right? Matter is neither created nor destroyed. So then another scientist, Joseph Proust, just a few years later, looked at people's data on compounds, right? So compounds like water or ammonia or nitrogen oxide and different compounds. And what he found was that the ratio of the elements was always constant when these compounds were decomposed, right? So for example, the mass of, let's say, carbon dioxide, right? If you look at the, which is CO2, the mass of carbon to the mass of oxygen, which were the two compounds, was always 2.67 to 1.33. Sorry, that's not correct. That's not what I want to do. Never mind. Let me do this one. Let's do ammonia, NH3, mass of nitrogen to mass of hydrogen, right, is 4.7. Okay. And someone asked me earlier, well, how do you use that as a conversion factor to get from the mass of one to the mass of the other? Well, remember, what does this mean? It means 4.7 grams of nitrogen to every 1 gram of hydrogen, right? 4.7 grams of nitrogen to every 1 gram of hydrogen. So if you know the grams of hydrogen, you can use it as a conversion factor to get to nitrogen, or vice versa, right? So for example, let's say you have 10.0 grams of nitrogen, right? You can write 1 gram of hydrogen to 4.7 grams of nitrogen. That cancels, and that would give you grams of hydrogen in this particular sample that had that much nitrogen. All right. So that's the law of constant composition of definite proportions. All right. Okay. So from a molecular point of view, right, if we look down at the particulate nature of matter, the reason that we have a law of conservation of mass is because when you have a chemical reaction, if the matter is made of atoms and if the atoms can't be created or destroyed, then you have a certain amount. Let's say this is sodium plus chlorine makes sodium chloride. If you have a certain amount of sodium and you have a certain amount of chlorine, and those are made of atoms, and those atoms can't be created or destroyed, right? So those atoms join together to form the sodium chloride. So the mass of those atoms at the beginning must equal the mass at the end, right? The law of definite proportions, if matter is particulate, right, you have compounds that are made of atoms, and those ratios are always the same, right? So in this case, you have 2 hydrogens to 1 oxygen. So since their ratio is the same in a molecule, therefore their mass ratios is always going to be the same, right? So this idea that matter was made of atoms, right, is sort of consistent with these laws, okay? So again, I want to remind you, observations, right? In this case, the observations on burning things or the observation on the masses of elements within compounds led to what? Laws, right? What were the laws? the law of conservation of mass, and the law of definite proportions. And then based on that, John Dalton built a theory or a model, right? Remember what a model or theory is. It's a framework, right, for how nature is, yeah? And so it's different than laws and it's different from the laws and observations. Remember, theories are what ultimately we're after. It's sort of the funnest part of science, right? Because you get to, scientists build a model for how they think nature is, right? And in this case, Dalton said, these laws and these observations are consistent with all of matter being particulate, all of it being made of particles, right? One of the most powerful ideas in all of science, right, came at this time from these observations and laws. All right. So what did John Dalton say? And again, you kind of watched a video on this, so I'm not going to go through this in too much detail, but every element is composed of these tiny particles called atoms, right? All atoms of a given element have the same mass and other properties. Turns out this is not true. All right. And we'll see why that is in a minute, even though that was part of John Dalton's original atomic theory. And the reason it's not true actually is because of isotopes, right? And you already saw a video on that as well. So we'll talk about that more in a minute. Atoms combine in simple whole number ratios to form compounds, right? And then lastly, number 4, atoms of one element cannot change into atoms of another element. In the reaction, they just change how they're bound together. This also is no longer true. So now we can do this with nuclear chemistry. We can actually change atoms of one element to atoms of another, okay? But at the time, this was the heart of the atomic theory. And the main thing here that you want to carry away is that matter is particulate. It's made of particles. Notice when he suggested this 200 years ago, it took 100 years, roughly, for it to be completely accepted and sort of proven as correct, right? Or validated as correct, all right? And his idea explained this Brownian motion that had come up in 1827, right? Earlier in that same century. So again, Einstein built his little model in 1905 that explained how atoms caused that Brownian motion. And then Jean Perrin confirmed it. And then in 1926, he won the Nobel Prize for that. And ever since then, you know, we've sort of been convinced that matter ultimately is made of atoms. It's particulate. Okay. Any questions on that so far? Questions? If you, I see that there's a thing in the chat here about making the screen bigger. I can't really make it any bigger than it is. What you can do though is if you can, the little thumbnail that has the people's pictures and maybe your picture, if you hide that thumbnail video, it'll actually make your screen bigger. So you can try that. I really am maxed out for room here, so I can't really make it any bigger. Can most of you see this though? Can most of you see this writing? Just nod. Okay, great. All right, so now once we learn that atoms, try fit on the screen option. Yeah, if I do that, then I lose this part. So not, again, there's not much I can do about that. I've played around with it a lot. All right, let's move on. Oh, I see. That there's some comments on the chat you might want to look at if you're having trouble seeing this. You can maybe make it bigger on your own screen. All right. So once we've learned that matter was made of atoms, then something interesting started happening, because remember, the idea was that atoms were indestructible, right? Atoms were these little particles that were indestructible, and that matter was ultimately made of those, right? But then in 1897, people started learning that, wait a minute, these atoms can be chipped. Little parts of them can be taken off. So this was discovered in 1897 by J.J. Thomson. He used a cathode ray tube. The cathode ray tube is basically just a tube like this. It's been evacuated. What does that mean? That means the air has been taken out of it, right? and then one side is negatively charged with using a voltage, right? So you have negative charge over here, and then you have positive charge on the other side over here, right? And what they found was that there was these little particles emitted from the negatively charged side that then flew through the vacuum towards the positively charged side, right? These really tiny particles that seem to be much lighter than atoms themselves, right? And there was a few things about these particles that were important. They were called cathode rays. They were independent of the material. And what I mean by that is it didn't matter what you made this out of, the cathode rays were the same, right? So if these were atoms flying across, right, then you'd see different particles for different elements, right? Because different elements are made of different atoms. But that wasn't the case. It didn't matter what you used here, the particles were the same. So that's why people started saying, oh, wait a minute. Atom itself is made of still more fundamental particles, yeah? That's what this suggested, right? They traveled in straight lines. And most importantly, they had negative electrical charge. How did they know they had negative electrical charge? Because they traveled from negative to positive. And the larger you made this charge difference, the faster they traveled, so the harder that they were pushed, in other words, all right? Now, you may have not heard much about or know much about electrical charge. We haven't talked about it yet, right? But electrical charge is a fundamental property of some particles in nature, all right? This thing called electrical charge. So it's kind of weird to think about, but it can either be, things can either be positively charged, negatively charged, or neutral, in which case they have no charge, all right? So the important things about electrical charge are, first of all, that positive and negative charges attract each other, okay? So negative and positive come together. Positive and positive or negative and negative repel each other, all right? So they're forced apart. And if you have a positive and negative together, they neutralize each other so that there's no charge, all right? The matter around you that you see right now is largely charge neutral, all right? There's really no charges in matter. Matter is largely charge neutral, which means that the positive and negative components of matter are in exactly the same quantities, right? Exactly the same number, so that they cancel each other out and the net charge is zero. If matter was charged, it would be totally different, all right? And you can get a little taste of this, perhaps by walking across a carpet on a dry day. You ever notice that when you walk across a carpet on a dry day, sometimes you actually acquire a little bit of charge, right? It's because you're rubbing, your feet are literally rubbing electrons off the carpet, and you get a few extra electrons in your body, right? And what happens? Sometimes your hair can start to stand on end. Have you ever had that experience? Right? And if you touch something metal, you'll get a zap, right? What's that? That's the charge neutralizing, right? Because you've acquired a little bit of charge, all of a sudden, matter is very different. There are some more extreme examples of that. If you've ever been in a thunderstorm, right? What's happening in the thunderstorm is you have these big thunder clouds, and as particles move in the thunder clouds, they rub against each other. And when they rub against each other, they rub electrons and charge off, right? And so all of a sudden you get a separation of charge within that thundercloud. And that separation of charge causes, at some points, can then have to equalize itself, right? And equalizes itself, you get a big lightning strike, and you get, of course, thunder and all that. So matter is generally charge neutral. When it's not charge neutral, things happen, right? Really dramatic things like thunder and lightning, okay? Questions? Any questions so far on this? Does that make sense? Characteristics of charge.
So is that basically what static electricity is?
Yes, yes. Static electricity is you accumulate charge. That's exactly right. Yep. What else? Other questions? Okay, so what did J.J. Thomson do? Not only did he discover these particles, right, but he also discovered the charge to mass ratio of the electron, right? So sorry, these particles were called electrons. I forgot to say that, right? They have negative charge, right? They're negatively charged. And by doing this experiment, he was able to measure the charge to mass ratio. What does that mean? The value of the charge divided by the mass. What did he do? He had a cathode ray, just like the previous one that we talked about, but he built it in a apparatus in which he could have it exposed to electric and magnetic fields. So this is supposed to be a magnet. This is supposed to be a charge here. And what happens is that these charged particles react to magnetic and electric fields, right? So they're churned or they're curved and they're bent, right? And the amount that they're bent depends on this charge to mass ratio, okay? And so by seeing how much they were bent for a given amount of field, and you don't have to worry about the details of this too much, except that he measured it, right? And he came up with this number, negative 1.76 times 10 to the 8th coulombs per gram. All right, that was the ratio of the charge of the electron to its mass. And this, we all know grams already. C stands for coulombs, and coulombs are a unit of electrical charge. Okay. Now, what did this imply? This implied that these particles were very small and not very massive. In fact, this implied, and J.J. Thomson, thought about this. He thought, oh my goodness, these particles are 1/2000th the mass of the lightest known atom, right? They're 1/2000th. In other words, it would take 2,000 of these particles to make up the mass of the lightest known atom, which was hydrogen. All right. So he built a model of the atom based on this idea. Okay. And we'll come back to that model in just a minute, but keep that in mind. He discovered these small particles, they make up the atom, and he also discovered and thought that the mass of them was about 1/2000th the mass of the lightest atom. All right. So what happened next? Robert Millikan in the early 1900s then did an experiment called the oil drop experiment, which is also very famous. And using that experiment, he was able to determine the actual mass of an individual electron. All right, so here's what he did. He took these little oil droplets, he squirted them into this container. This is kind of like, you don't see these very much anymore, but in the old days we used to have these perfume atomizers where it's just like a little bulb and you squeezed it and it made little droplets of perfume, okay? So this is what he was basically using. It made little droplets of oil, all right? These little droplets of oil then fell to the ground under the influence of gravity, right? But then as they were falling, he hit them with ionizing radiation. And all that means is that he was able to create electrical charge in them. So you can think of it this way. These particles began to acquire electrons. Kind of like you acquire electrons when you walk across the carpet on a dry day, right? Some of the electrons enter your body and you get what we call static electricity. These particles were doing the same thing, right? They were getting extra electrons, so they were acquiring charge. And what he could do is he could levitate them. He could stop them from falling by putting electrical charge on this plate, making that negatively charged. And basically what he figured out is if he knew the weight of these particles, he could figure out how strongly they fell due to gravity. And then by figuring out how much charge he had to put on them to stop them from falling, he was actually able to measure the charge on each individual particle, on each individual droplet, right? The actual electrical charge. So he got things like this. One drop, for example, had this charge. Remember, here's the C again, coulombs. It's a very small number because electrons are very small, but this drop had Negative 3.2 times 10 to the minus 19 coulombs was its charge, right? Another drop had this charge, another drop had that charge, another drop had that charge, right? So he was able to measure the charges on these different drops, okay? Well, why was that important? Well, remember that electrons are particles, right? So they come in units of 1, 2, 3, 4, 5, 6, 7, or something like that. So each of these drops had to have some integral number of electrons, right? So the largest common factor, in other words, the factor that is largest and divisible in all these must be the charge of the electron, right? And so by making these measurements, he was able to do so. The charge of the electron was negative 1.6 negative 1.6 times 10 to the minus 19 coulombs, right? He was able to figure that out. And then, of course, if you know the charge and you know the charge to mass ratio, right, then you could also get the mass. And the mass of the electron was 9.10 times 10 to the minus 28 grams, right? Super, super small, right? And had this tiny charge. Now, you might be thinking to yourself, oh, wow, okay, why is this important? You know, why do we want to know the charge of the electron anyway, right? It's a beautiful day. Why aren't we at the beach instead of learning about the charge of the electron, right? Well, if we think about it a little bit, we can see actually how important this is, okay? What if electron charge was a little, let's say, smaller than that? What if electrons had a smaller charge than minus 1.6 times 10 to the minus 19 coulombs? Well, what does the electron charge determine? It determines how strongly it's attracted to the nucleus of an atom, right? It determines how tightly electrons hold atoms. So you can imagine if atoms held electrons less tightly, right? Atoms themselves might not be stable. Imagine that. What would happen if atoms weren't stable? Well, if atoms aren't stable, then we'd have no atoms, we'd have no molecules, we'd have no people, right? We'd have no planet, we'd have just a bunch of fundamental particles, right? So we could think about it the other way too. What if the charge was a little bigger, right? What if the charge that Millikan had measured was, you know, a lot bigger than this number? Well, then what would happen? Electrons would be held what? By atoms. More tightly or more loosely?
More tightly.
More tightly, yeah, exactly right. They'd be held more tightly, right? If they were held more tightly, then maybe we wouldn't have any chemical bonding, right? Because remember, chemical bonding is the sharing of electrons between atoms, right? If they were held more tightly, we might just be stuck with 100 or so elements, right? And no molecules. Well, no molecules, again, we're mostly molecules, right? No people. So again, that's why the characteristics, right, of these fundamental particles is hugely important. Why? Because it determines everything down the line, right? Determines everything down the line. So that's why, you know, this number is so important, right? It tells us the charge of the electron. It determines how tightly atoms hold on to their electrons. Any tighter, they might not share them, or we might not have chemical compounds. Any looser, and the atom itself might not be stable, right? All right, questions? Is that clear? All right, no questions. Good. All right. So now we knew this idea that that atoms contain these other particles, electrons, right? Because we had discovered them. So now the question is, well, what is the structure of the atom? If atom is composed of even smaller particles, how do those fit together, right? So remember, J.J. Thomson thought that even the lightest atom contained how many of these particles? Or what was the mass of this particle compared to the smallest atom? Remember from earlier? Anybody?
1/2000?
Yeah, 1/2000, right? So he actually thought that the lightest atom maybe contained 2,000 of these particles. Okay? So he came up with a model called the plum pudding model for the atom. Now, most of us are from the United States. Some of you may have been to the UK. Some of you may have traveled around the world, but in the United States, plum pudding is not very common. All right? Plum pudding is super common in the UK, and it's a British dessert. All right? And it's basically made up of plums in kind of a custardy thing. So for us, maybe plum pudding is not the most descriptive term. Maybe we could call it the blueberry muffin model. All right? Because for us, we're probably more familiar with blueberry muffins than we are with plum pudding. But in this model, you have this sphere of positive charge. Now, this sphere of positive charge was just positive charge in a spherical arrangement. It didn't have any particles associated with it. And in that positive charge were held all these electrons, right, that were negatively charged. And it took a lot of them to make up the mass of an atom, right? And so that was J.J. Thomson's model, right? The plum pudding model, or for us, maybe the blueberry muffin model. So models, remember the scientific method, right? When you have a model, what do? You test it through what?
Experiments and observations.
Yeah, experiments and observations. So now we got to go back and say, okay, does this model hold up to experiment, right? At that time, scientists had discovered a phenomenon called radioactivity, which we'll get back to much later in this course at the end of next semester. But all you really need to know about radioactivity is that these are particles that are emitted from the interior of atoms, okay? And there are three types of these particles. Alpha are the most massive. An alpha particle was about 7,000 times as massive as an electron. All right? So if you were to compare the mass of an alpha particle to the mass of an electron, it would be like the mass of a cannonball compared to the mass of a ping pong ball, right? Just to get an idea, all right? So the alpha particle is this hugely massive particle, the mass of a cannonball. An electron, in comparison, would have the mass of a ping pong ball. All right, and there was a couple others that were discovered as well, but this is the one we're mostly interested in. And by the way, Marie Curie, who we'll hear about more as we go along here, was one of the people involved in discovering this. So then people set out to test this idea, to test this model of the atom. And the experiment they set up is now known as Rutherford's gold foil experiment. And what Rutherford did is he took a piece of gold foil, he pounded it really, really flat, almost to the point of it being transparent, okay? And then he shot alpha particles at the gold foil. So you can kind of think of it this way. If this gold foil was made of atoms, and if those atoms were the way that Rutherford envisioned them in the plum pudding model, right? Then what you're doing is you're shooting cannonballs at a wall of ping pong balls, right? Because these atoms were composed of this massive number of electrons, right, in the sphere of positive charge. And if you throw a cannonball at it, right, it's just going to, what's it going to do you think? What do you think Rutherford expected?
Just go clean through.
Yeah, go clean through, right? Imagine shooting a cannon at a wall of ping pong balls, right? Just blast right through, right? So that's what he thought. And again, remember, he was testing this idea. He was trying to determine, okay, is this idea valid, right? Does it agree with the experiment? So he started doing this experiment, and sure enough, a lot of these alpha particles went right through, right? And he can detect them, and most of them ended up here. But some of them were deflected. And he's like, that's kind of weird. How do ping pong balls deflect a cannonball? Well, maybe they could deflect them a little bit, but then occasionally he noticed that some of these actually bounced backwards. And that really screwed up the plum pudding model, right? The plum pudding, there's no way the plum pudding model could be true. Imagine this, again, you would have to say that shooting a cannonball at a wall of ping pong balls and the cannonball would bounce back, right? That made no sense whatsoever. In fact, here's what Rutherford said. He said, these results are about as credible as if you had fired a 15-inch shell at a piece of tissue paper and it came back and hit you, right? How is that possible? Well, it wasn't. So what happens when the experiments don't back up a theory, right? What happens when the experiments don't agree with the model? What do you do to the model?
Revise it.
You revise it, right? You revise it and you come up with a new model. So Rutherford came up with a new model, and that model is called the nuclear model. The nuclear model for the atom. And it was very different. In the nuclear model, all the mass of the atom is scrunched up in a really tiny space in the very center of it. That tiny bit of matter at the very center is called the nucleus, all right? It's a small core, and all of the mass and its positive charge are in this nucleus, all right? So you have this sort of nucleus, right, that has all the mass of the atom and all the positive charge, right? All that contained in this thing called the nucleus. And then he said, most of the volume of the atom must be empty space through which tiny negatively charged electrons are dispersed. So these electrons, instead of making up the mass of the atom, they were only a very small fraction of the mass of the atom. And they existed kind of out here, right? And I'm not drawing this to scale. If this was a nucleus, if this was a real nucleus, this electron cloud would have to be as big as your house, right? Or even bigger, okay? The nucleus is a very, very small part of in terms of the size of the atom, but it has all the mass, okay? And then he said there is as many negatively charged electrons outside the nucleus as there are units of positive charge inside the nucleus, okay? So, so that was Rutherford's nuclear model. In other words, this is what Rutherford thought. Sorry, this is what J.J. Thomson thought, the plum pudding model, all right? Electrons would have just gone, these alpha particles would have just gone straight through this. Here is Rutherford's model, the nuclear model. Most of the mass is right here. Most of the volume has these tiny electrons dispersed through that volume, but not much mass, right? So if these alpha particles go through this part of the atom, they just go right through. If they go close to the nucleus, they can get deflected a little bit. Once in a great while, they hit the nucleus and they bounce back, all right? It's important to get a feeling for what the relative scale is here, right? Imagine a huge stadium, right? Like maybe Dodger Stadium, right? In LA. If the nucleus if Dodger Stadium was the size of an atom, let's say an atom was the size of Dodger Stadium, then the nucleus would be about the size of a mosquito in the middle, right? That's how much, that's how much, so this is the mosquito, this is the stadium, right? There's mostly empty space in the atom, all right? And only this very small, dense part in the middle, okay? And what we've learned is that this model is very successful, right? It predicts it predicts everything about matter, and it is accepted and valid today, right? So you might say, wait a minute, how is it that, you know, matter, even paper, right, or cardboard seems pretty solid, but yet it's mostly empty space, right? In this matter, there's tiny nuclei where all the mass is, and then there's a lot of empty space in another tiny nucleus, and a lot of empty space in another tiny nucleus, right? Within this, okay? How can that be? Why does it look so solid? Well, you can think of matter kind of like a big jungle gym like this, right? Jungle gym, imagine a jungle gym the size of a football field, okay? And now imagine seeing that jungle gym from the air when you're flying over it at maybe 3,000 feet. When you look down at that jungle gym from really, really far up, right? How does it appear? Can you see all the empty space very well?
No, probably not.
No, probably not. It's going to kind of appear like a solid mass, just like this looks like a solid mass to our eyes, right? But in reality, this jungle gym, right, is mostly empty space, okay? And so that's why matter appears so solid. Now, what would matter be like if the structure of the atom were to break down? In other words, what if we just had, what if matter, instead of being this way, right, was just nucleus, 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 right, all positively charged? What would happen if nuclei were like right next to each other and touching each other? How would that kind of matter be different from the matter we experience today?
Super dense.
Super dense, exactly right. It would be unimaginably dense, right? A single head of a pin would weigh millions of pounds if that was the case, okay? And in fact, there are some places in the universe where matter has broken down and it does have this structure. Anybody know what those are called?
Neutron stars?
Yeah, neutron stars or black holes, right?
Okay.
Black holes, neutron stars, that's where the structure of atoms has actually broken down, and what you have is boom, 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 solid nuclear material, yeah? And again, if you had a little piece of that, of a neutron star, right, the size of the head of a pin, it would weigh 11 million pounds. Imagine that. A head of a pin weighing 11 million pounds, right? So that gives you an idea for how matter is and how much empty space really is in matter, okay? Questions for me on that? Does that make sense?
I have a quick question.
Yeah.
So is that why there's variation in density between different like substances?
Great question. That is more of a matter of actually we're gonna talk about that a little bit later. But no, only matter is only like this in weird places in the universe, right? Like you'll never encounter matter like this on Earth. All right. The reason there's difference in densities is because atoms have different sizes and they have a different relative mass to their size. All right. And the relative, and actually as you go down the periodic table towards the bottom, the mass gets heavier faster than the size gets bigger. Okay. And so things at the bottom of the periodic table tend to be more dense than things at the top of the periodic table. That's really because of the size of the atom and the weight of the atom. It has really nothing to do with this. This is very, very odd, and you would never encounter this on Earth. You'd only encounter this in a neutron star or a black hole. And then the gravitational forces around this kind of matter are so intense that you'd be, if you ever got close to one of these, right, you'd get sucked right in, and then all your atoms would become like this, and then that would be the end of us, right? If we ever did that. So avoid those places, right? If you're traveling around the universe, stay away from neutron stars and black holes. All right, other questions? Any other questions?
So does electrons have the same charge as protons?
Yes.
Even though they're so much lighter?
Exactly correct.
Okay.
They have the same charge in terms of the magnitude of the charge, but opposite in sign.
Okay.
Right? The proton is positively charged. The electron is negatively charged. They exactly cancel each other out. All right. But the proton has all the mass, and the electron has very little mass in comparison.
Okay. Even though it has the same charge magnitude.
Correct. Yes. Exactly
Okay.
right.
Okay.
Yeah. Yep.
I have a
Great
question.
Other questions?
If
You raise your hand. If you raise your hand in, do you know how to raise your? If you don't, just go ahead and speak. But if you raise your hand, then I can see your name and I can call on you.
Oh,
if you don't mind. Yeah, okay, let's see. Is that Michael?
Yeah.
Great. Michael.
I just wanted a clarification on protons. So all protons, like regardless of what matter they're associated with, they all protons have the same charge?
Correct. Yep.
Yeah.
And
Okay.
and it's exactly so. A proton. So if this is the charge of an electron, right? What's the charge of a proton?
The same but opposite charge?
Exactly. So the charge of a proton would be positive 1.6 times 10 to the minus 19 coulombs.
Okay, cool.
Happy coincidence, right?
Yeah.
If that wasn't the case, then we'd have matter with residual charge, right? They couldn't cancel each other out. And if you have matter with residual charge, like I said, imagine being in a thundercloud, right? That's a very different kind of matter, very, very unstable.
Yeah, thank you.
Any other questions? One sec. Close my door here, a little bit of noise outside. Okay, so let's go look at all the different subatomic particles. So actually, for purposes of chemistry, we only have to worry about the proton, the neutron, the electron. Turns out that the electron is a fundamental particle. You can't break the electron down in any simpler particles. From physics, we know that the neutron and the proton are not fundamental, right? They can be broken down into more fundamental particles like quarks and things like that. For the purposes of chemistry, we don't really have to worry about quarks. We just have to worry about these three particles, all right? But it's good to know that the electron is fundamental. There's nothing else smaller than the electron within the electron. Protons and neutrons, it turns out, they're made of even more fundamental particles, right? And but again, for chemistry, we really don't have to worry about those, all right? So your proton has this mass in kilograms. We're going to also be using the unit of atomic mass units. So the proton has a mass of about 1 in these units, which is kind of convenient. A charge of +1 on the relative scale, or 1.6 times 10 to the minus 19 coulombs in coulombs. All right. So we'll be using both of these scales. All right. The neutron, notice very, very similar mass to the proton. Okay. You can see the similar mass again here in this unit, about 1 atomic mass unit, but it has no charge. All right, the neutron is neutral, and so it has 0 charge. The electron, much, much less massive, right? Very, very small mass compared. If this was the mass of a baseball, right, this would be about the mass of a grain of rice, just so you get an idea, right? So most of the mass is really here and here. These are very, very light in comparison. But the charge is exactly opposite of the charge of the proton. Here's the conversion factor between atomic mass units and kilogram. All right. So now we know what are atoms. They are protons, which are positively charged, right? And neutrons, which are neutral, right? Those all occur in the nucleus. Most of the mass is there, right? And then electrons outside. So how does one atom differ from another? Well, it turns out it's just in the numbers of these particles. All atoms are made of the same 3 particles. The way they differ from one another is just in the numbers of those particles. Okay? So here's helium. Helium has 2 protons in its nucleus. Carbon has 6 protons in its nucleus. All right. Neutral helium, since it has 2 protons, must have how many electrons? 2. Yeah, 2. And carbon has 6 protons, so how many electrons?
6.
6.
6.
Okay. So this number, the number of protons, is a super important number. It's called the atomic number. Right? And it's the number of protons in the nucleus of an atom. Okay? The number of protons in the nucleus of an atom. And it's given the symbol Z. All right? Each element is represented, is given a name, like helium and carbon, right? And all carbon atoms have 6 protons in their nucleus. All helium atoms have 2 protons in the nucleus. This is all summarized in the periodic table. All right, so look at the periodic table in your ebook or in your printed book if you ordered the printed book. Each element has a chemical symbol, like in this case, beryllium is Be. It has a name and it has atomic number. The atomic number tells you what? The number of protons in the nucleus. Okay. So here's helium, right? It has 2. Here's carbon, it has 6. Okay. You might be wondering where the names of atoms came from. Well, in the early days, the people who discovered them were able to name them. Some of them gave them names based on their properties. So for example, chlorine comes from the Greek chloros, which means greenish yellow. Why? Because chlorine was a greenish yellow gas. All right. Argon comes from the Greek argos. Argos means sleepy or sleep. That's because argon was an element that didn't react very much. So it was kind of sleepy, right? And that's how they named it. Other people named elements based on their country. So for example, Madame Curie discovered polonium. She named it after her home country, which was Poland, right? You can see some others named after europium, named after Europe, right? Here's berkelium, named after
Berkeley.
Berkeley. Yeah, it was discovered at UC Berkeley. Californium. Hey, we're the only state that has an element named after us, right? That was also discovered at Berkeley. Some elements are given the names of people, like curium here, Einsteinium, fermium, Mendeleevum, right? Those are all named after people, okay? Some symbols don't really match the name very well because the symbol is based, in this case, on the Latin name natrium, all right? So when you're looking at elements, you know, kind of take a look at the periodic table, and you don't have to memorize it, certainly, but be familiar with it, right? And be familiar with things like this, all right? Okay, isotopes. So we know that all atoms of a given element have the same atomic number, and therefore the same number of protons, right? But they don't have the same number of neutrons, all right? So A is called the mass number, and it's equal to the sum of the number of protons plus the number of neutrons, okay? And that's called the mass number. So all atoms of a given element have the same atomic number, but they may have different mass numbers, right? And you saw this in the video, right? So the pre-class video today talked about isotopes. So for example, neon, all neon atoms have 10 protons in the nucleus, right? But some have 10 neutrons, some have 11, some have 12, okay? And so they're gonna have different mass numbers. Notice mass number is the sum of both of those, right? So 10 plus 10 is 20, 10 plus 11 is 21, and so on, all right? Within a given sample of neon, these are distributed according to some natural abundance. So in naturally occurring neon, right, you'll find that there are 90% of those atoms are this isotope, a very small fraction, less than 1% of this isotope, and then about 9% are this other isotope, right? And those are called isotopes. Yeah, I should just go ahead and define that. Isotope, atoms with same number of protons, but different number of neutrons. All right. Okay, so there's a way to specify these, and that's with this symbol right here, XZA, right? Where this is the chemical symbol for the element, this is the atomic number, right? And this is the mass number, right? So you can specify any isotope using this notation, all right? So for example, here is the isotope notation for a particular isotope of chromium, right? And what can you tell me about that isotope of chromium? First of all, how many protons?
24.
24.
24, yeah, 24. So 24 protons, okay. How many neutrons?
28.
28. How do you know that? You subtract this from this, right? Because this is the sum of both the protons and the neutrons, right? So number of neutrons is 52 minus 24 equals 28 neutrons, okay? And if this is a neutral chromium atom, how many electrons must it have?
24.
24.
24. 24 electrons, right? So you can get all the information from this kind of notation. Does that make sense? Questions? All right, I'll have a question for you then. Go ahead and try this. And just this notation is, you saw from the video, hopefully it's the same idea, platinum 192, right? You need to know that platinum is atomic number 78, right? So if we were to write that in the other notation, it'd be platinum 78 192, okay? This and this mean the same thing. So go ahead and try to answer that question. Okay, almost everyone's done. I'll give you a few more seconds here. All right, so almost virtually all of you got that right. Very nice. 78 protons, 78 electrons, right? Because it's neutral. And then 114 neutrons, and you just get that from subtracting 78 from 192, and you get 114. So very, very good. Awesome. All right, let's move on. Atoms can lose or gain electrons to form ions. So an ion, definition of an ion is that an ion is a charged particle. Sorry, let me, ion is a charged particle, all right? And it can be an atom or a group of atoms that have lost or gained electrons, right? So for example, lithium, the lithium atom can lose an electron, and we can sort of symbolize that like this, right? To become Li plus an electron, right? Remember, lithium is charge neutral. All atoms are charge neutral, but if they lose an electron, right, they become positively charged. And if they gain an electron, what happens?
Become more negative.
Yeah, so fluorine, for example, can gain an electron to form F minus, right? This is a positive ion, and this is a negative ion, okay? Positive ions are called cations. Negative ones are called anions, okay? All right, so let me ask you a question here and see if make sure you're getting this. Go ahead and try to answer this. All right, try to finish up here in the next few seconds. Okay, so what did we get here? So let's see, 70% of you put D and a few of you put A and a few put B, right? So what's going on here? So if you think of sulfur, right? Sulfur, you can tell from the periodic table, right? That neutral sulfur has how many protons?
16.
16
16.
protons, right? 16 protons. So neutral sulfur would have how many electrons?
16.
16 electrons, right? In neutral sulfur. Now you have sulfur 2-, right? Which means that it has 2 extra units of negative charge. If it has 2 extra units of negative charge, then how many electrons must it have?
18.
18. Okay, so it's 18 electrons. Those of you that put A accidentally subtracted 2 instead of adding 2, right? But remember, if it has extra negative charge, it has extra electrons. If it has extra positive charge, it has fewer electrons in the neutral atom. Okay? Does that make sense? All right. Very good. Let's move on to a little bit of introduction to the periodic table and the periodic law. So first of all, remember we were just talking about density a little bit ago, and I was telling you how the density of a particular atom depends on the ratio of its mass to its volume, right? So essentially the density of a material like aluminum depends on the density of aluminum atoms, right? Which is the mass of an aluminum atom divided by its volume, right? So notice here is a column from the periodic table: boron, aluminum, gallium, indium. And look what happens as you go down. First of all, look what happens to the radius of the atom. It gets bigger, right? And then notice what happens to the density of the material. It also gets bigger, okay? So even though the atom gets bigger, its mass gets bigger faster, right? Which is why you see this. This is an example of a periodic property. The radius of the atom is an example of a periodic property. It varies in a sort of predictable way from the periodic table. So there was a Russian scientist by the name of Dmitry Mendeleev, okay? And now we're going to see the same pattern coming up again that we've seen before: observation, law, theory, right? Keep that ingrained in your mind because we just revisit this over and over. So in this case, people made some observations. What kind of observations? They were looking at the properties of elements, things like their radius, for example, or their reactivity, like how did they react, right? So they were looking at these properties of elements. And so there was all these observations on the properties of elements, right? There's the first step of the scientific approach to knowledge, right? Observation. Mendeleev came along and he noticed a pattern. And by the way, this is what kind of makes great scientists, right? A great scientist notices a pattern that other people missed. So this data was all out there, right? during Mendeleev's time. But Mendeleev is the one that noticed the pattern, right? And that pattern he summarized in what's now called the periodic law. And the periodic law basically says that when elements are arranged in order of increasing mass, certain sets of properties recur periodically. Okay, they form this periodic pattern. So let's say this little set of tiles here. Here are all the elements listed in order of increasing atomic number, right? Which is roughly the same as atomic mass. And these colors are representing one of their properties. All right. So notice what happens: tan, green, blue, purple, right? And then you go, and then again you see tan, green, blue, purple. Tan, green, blue, purple, right? That's what it means to say that it recurred periodically, right? When you list the elements that way, you see the same pattern come up over and over again, right? This periodic nature of these properties. Yeah? So what Mendeleev did, he said, well, wait a minute, why don't I organize all the elements? And there was, I think, something like 60 or 70 of them known at the time. So why don't I rearrange this to make a table so that all the tan elements line up in a column and all the green elements in another column and so on, right? So he took his periodic law and he used it to make a table kind of like this, right? And notice that now elements with similar properties end up in columns, okay? And so this was kind of the first periodic table, right? And Mendeleev, when he made his first sort of periodic table, he noticed that there were some missing elements. There were some holes in his table. So imagine that 60 elements have been discovered out of 100 and something that we know now. And at the time, Mendeleev just puts together this. From his law, he puts together this table, right? And he says, wait a minute, there's some missing holes here. What did that mean? What did it mean that there were some missing holes in this table? There were some missing elements in this table. What did that mean? What do you think it meant?
The transition elements.
That there were additional elements that had not yet been discovered. That's exactly right. So in other words, Mendeleev predicted, he said, hey, you guys who are out there looking for elements, go look here because there are some missing ones. And sure enough, he was right. All right. And not only did he predict that they should exist, he also predicted some of their properties, believe it or not. Right. So Mendeleev predicted that, for example, this element, which he called aluminum, which we now know as gallium, he predicted its atomic mass to a pretty low degree, to a pretty close amount. He predicted the melting point. He predicted the density. He predicted the formulas of some of its compounds, right? And all of this was correct, right? He also predicted the existence of germanium, which he called ecosilicon. And again, the same thing, right? All from this one idea right here, right? That he saw that no one else saw, right? This pattern that he saw. So he was able to put together the periodic table, which we all sort of know and love today, right? And this is a more modern example of the periodic table right here. Okay. All right. I think I'll stop here and we'll start here on Wednesday. We have a couple more minutes. Are there any other questions on anything from today? Are you raising your hand, Asher? Asher Wynn?
Yes.
Yes. Okay. So I saw you physically raising your hand, but remember, it's easier for me to see you if you use the raise hand function in Zoom.
I was going to ask about that. I don't know how to use it.
If you go to participants.
Yeah.
Wait a minute. Actually, from your end.
This says invite.
Sorry, could someone else actually
Yeah.
I'm not sure how to do it from your end.
Yeah.
Once
hold on.
you click participants, it should come up with all the participants and then have functions like raise hand, yes, no,
There
go
you go.
slower, go faster, more, and then below that
Oh,
it
I
says
see it.
invite,
Okay.
mute me.
Yep, perfect.
Don't-
So
Oh,
that's how you
okay,
raise your
okay.
hand.
Yeah.
Okay,
Don't
go ahead
click on
and
the
ask-
arrow.
Go ahead.
Yeah, I
I
see it.
saw
I
you
see how it
physically,
works.
Asher, so you can go ahead and ask your question.
Okay, so I actually had another question.
Yeah.
So for the last elements of the 100 teens or so, weren't they
Yeah.
like abbreviated with like 3 letters before?
Yes, but very good question. Yeah. So they were, because they had temporary names, but in the last couple years
It was theoretical.
they were actually given permanent names. Yeah, good observation. So these actually now have permanent names, and so that's why they don't have those funny abbreviations anymore, like unil hexium, right? UNH. They used to have names like that, but now the committee met and they actually were given permanent names. Good question.
I thought those were like more official though. Interestingly.
No, these are their official names now. Again, only in the last couple of years has that happened.
Right.
Yeah. Good. Okay, let's see. Javier.
Yes, I have a question about the mass number. When we have the mass number, only the mass number, is there a way we can actually calculate the mass of a particle, of a compound?
So roughly speaking, if you know the mass number, that's close to the mass of the atom, but it's not exactly the mass of the atom. So we'll talk more about atomic mass next time, okay? But no, the answer to your question is no. If you just know the mass number, you can't necessarily get the exact mass. It's close, right? So if you have a mass number of 120, the mass of that particular isotope is going to be about 120, but not exactly that, but close.
Okay, thank you.
Okay. Yeah. Let's see. Kaylee.
Hi, yes, it's Kylie.
Kylie, sorry, Kylie.
No worries. In the beginning of lecture, when you were going over kind of the history into chemistry today, I was just wondering if we were going to be tested on the specific names and dates of all of these.
Yeah, that's a good question. So what I want you to have, you don't have to memorize any dates, so that's good. What I want you to know is the basic development of these ideas, and so know the names of the scientists and their experiment and the significance of their experiment. That's what I want you to know. You don't have to know the specific dates and things like that, but you just need to know the ideas and the names of the scientists. Does that answer your question?
Yes.
Perfect. Okay, let's see. Anybody else? Okay, I don't see any more hands, so I think I'll officially end class since it is 3:20. Thank you for being here. Thank you for listening and for your participation, both in terms of questions and in terms of answering the polls. I hope you have a good afternoon, and I'll see all of you on Wednesday. If you need to see me this week, remember I do have office hours starting now, so you can hang around and ask me questions now. I have office hours tomorrow from 2 to 4 and Thursday 2 to 4 as well. I'd like you to email me for those, right? Just so they don't get so crowded. So just make sure to send me an email and I can meet with you during those times if you have other questions. And of course, I'm always available on email. And I know I say that I answer within 24 hours, but if you send me an email, you know I usually answer much faster than that. So thank you very much and have a great day. And I'll stick around. I'll just pause here for about a minute and I'm going to stop the recording and then I'll take any additional questions.
Thank you, Professor.
Thank you.
Thank you.
Thank you.